Oh, you won, yeah, for sure. What we're doing in this section is, actually the section is divided into two parts. There's sort of a visual representation where you use graphs and rectangles to calculate area. And then we kind of split off from that for a little bit, and we get into summation notation using like basically sequences. And then we bring it all back together. So this is kind of a pretty in-depth section that we're in right now, so it's very important that you try to understand every little thing that we're doing. Okay, so I have two situations here that are kind of mimicking what we looked at here with trying to calculate the area under a curve. So this region right here has an area that we're trying to calculate. You see squares here, you see rectangles here. With the squares, you cut up all the squares and then you tried to fit in all the little pieces that were left over. With the rectangles, you have two choices. You can make your rectangles go up to the curve and then over and back down, which would wind up leaving all of this leftover space here that we didn't account for that should be in our estimate. Or you can make your rectangles go up to the curve but wind up giving you excess area in your calculation. Both of those methods are completely valid. You just have to realize that one method gives an overestimate and the other method gives an underestimate. Okay? Now I'm calling this using left endpoints and using right endpoints. So let me get rid of all these little marks that I just put on here so that we can figure out what left and right endpoints means. Left endpoints means the left side of the rectangle that I'm creating comes up and touches the curve. So, for example, on this rectangle right here, the left side of that rectangle is this guy right here. And it comes up and touches the curve. Then it goes over and forms the rectangle and comes back down. The next rectangle is a part of, it's sharing this side right here, but then it's continuing to go up and touch the curve on the left side of that next rectangle. Then it comes over and comes back down. And each subsequent rectangle after that is formed in the same way. The left side of the new rectangle comes up, touches the curve, over and down. Comes up, touches the curve, over and down. Okay? Similarly, right endpoints, you're forming rectangles, but this time you're using the right side of each rectangle. So, right side of this rectangle here comes up, touches the curve, comes over, comes down. Same right side for my new rectangle comes up, touches the curve, over, down. Comes up, touches the curve, over, down. And then you go all the way through the region for the area that you're trying to calculate. Okay? Now there's going to be times where a rectangle doesn't have a height at all. Like over here. Using left endpoints, this curve actually is at 0, 0 right here. So for my left endpoint, I'm already there. I don't have to go up. I just go over and down. So what would the area of that rectangle be? 0, okay? Now, if you know the height of the rectangle and you know how wide each one of these rectangles is, then you can calculate the area of each individual rectangle and then add all those rectangles together and you will have a reasonable estimate for the area under the curve. Make sense? That's why we choose rectangles, because they're easy to calculate areas for. Okay. We could make a weird trapezoidal thing. We probably wind up calling that the trapezoidal rule. Probably. Yes, there is. So what you're realizing, what you're already realizing is maybe there's other ways that we can do this, and there are other ways we can do this. Rather than going with left endpoints or right endpoints, we could do maybe the midpoint where the center of the rectangle comes up and touches the curve and forms maybe a better estimate. That's a method. Or we could go with forming trapezoids, where the left side of the rectangle comes up and touches the curve. The right side of the rectangle also comes up and touches the curve, and then we connect those 2 points. Notice how much less error there is already just in that first one that I've created. Okay? So your random thought actually is true. The best method possible is called the trapezoidal rule for this type of situation, and we will study that down the road. For now, we're just going to concentrate on left and right endpoints. Okay? All right, a couple of important points down towards the bottom. Notice that the rectangles we drew are below the actual graph of y equals, this is y equals 1/2 x squared, incidentally. This is called the lower sum. It's called a lower sum because it's an underestimate. And then notice the rectangles are above the actual graph on this one. This is called an upper sum because we are creating an overestimate. And then in bold down at the bottom, by increasing the number of rectangles, this should be kind of an obvious point right here. If we make more and more rectangles, we'll get a more and more accurate result. So rather than these 1, 2, 3, 4, 5, 6, 7, 8 rectangles, we could maybe double the number of rectangles and have 16 rectangles. And if I did that, then this rectangle would be split, and I'd create all of these rectangles like so. And now I've reduced the amount of missing area that I should have accounted for by quite a bit. So I suddenly become much more accurate, okay? And then if I cut those rectangles in half again, I'd have 32 rectangles. Obviously, I'm getting more accurate, okay? So hopefully you can kind of see, based on your experience in this course, what we're going to be doing. We're going to coincidentally, because of the shape of this graph, yes.
Oh. Because it looks like you're still using it.
Yeah, coincidentally. If I keep going with smaller and smaller and smaller rectangles, it will give me more and more and more rectangles. And in the spirit of calculus, that means that probably what we're going to wind up doing is what?
Smaller.
Letting the number of rectangles go to infinity. And we'll take the limit as the number of rectangles basically goes to infinity. Okay? So that's how calculus is going to get back involved in what we're doing here, so that we can eventually find, if I take the limit as the number of rectangles goes to infinity, would that give me the perfectly correct answer?
No.
If I let the number of rectangles go off to infinity, what happens to my error here? Smaller and smaller and smaller, right?
But would it ever hit?
Until the error effectively goes to 0, which would effectively give me the perfect area. Okay? So that's where we're headed. So now that we know all that, I've removed all of the lines, and I want to calculate the area using endpoints. On the left one, we'll use left endpoints. On the right one, we'll use right endpoints, and we just need to decide how many rectangles we want to use for our estimate. 2? Come on. How about 4? Let's use 4, okay? Now, there's some things that we need to realize before we start making our 4 rectangles. How wide is each rectangle going to be? Because we need to find out how wide and how tall each rectangle is, right? How'd you do that? 0.5.
Well, you said we're going to 4.
Yeah?
And it's 2. So
What's 2?
Like
So from here,
the length of the region that we're trying to
the length of the region that we're trying to find is 2 units, okay? And I want 4 rectangles.
divide it by 4.
Okay, so what you did is you said this endpoint here minus this endpoint here, and I want 4 rectangles. Okay? I'm going to say it that way because if I had some shape that was like over here, and this was 1 and this was 3, then what would the width of each rectangle be? The same thing, because you did 3 minus 1 to find out that this overall length here is 2, and then I divide it by 4 to get my 4 rectangles. Okay? You follow that?
Yeah.
So we're going this endpoint minus this endpoint, divided by the number of rectangles that we want total. Make sense? Okay. So let me get rid of this then. And we know that our rectangles are going to be 0.5 long, so I have those as my divisions. Does that give me 4 rectangles? Yes. Now I'm using left endpoints, which means that the left side of each of these rectangles has to come up and touch the curve, and then I go over and back down. So for this first one, I start with the left side. It doesn't go anywhere because the function seems to touch 0, and then it goes over and back down. Okay? The next one starts at the same endpoint, the right side endpoint of my first rectangle, goes up, over, and down. And then up, over, and down. And then up, over, and down. Very inaccurate, yes, because we're only using 4 rectangles, and you guys wanted to use 2. We could make it more accurate by using 8.
12.
Okay, sure, 20, 50, 152. But we're not going to, okay? What I'm going to do is show you guys a trick on how to do these. I think it kind of helps. We're using left endpoints, so below my figure here, or for my work that I'm going to show, I'm going to draw rectangles that are just showing the lower left corner, the lower portion of those rectangles, okay? This bar is here because of the fact that I'm using left endpoints. This would be the width of the rectangle that I'm showing here, okay? Now we know that the width of each rectangle is how much? 0.5. What I'm going to do now is calculate the height, and I'm going to write the height of each rectangle down here, okay? Now the function that we're given, I told you on the previous page, was y equals 1/2 x squared. I need to calculate the height of each rectangle, which means I need to find out where the function is at each of these left endpoints. So we're going to plug in the left endpoint here. Okay? Plug in 0, and I get 0. So my height here is 0. Plug in 0.5, which is 1/2. 1/2 squared is 1/4. 1/4 times 1/2 is 1/8. Make sense? Okay. Next one, the left endpoint is 1, so 1 squared is 1 times 1/2 is 1/2. And then finally, 1.5 is 3/2. 3/2 squared is 9/4. 9/4 times 1/2 is what? I'm not doing all the thinking. 9/4 times 1/2. 9/8. Okay, so this is the process that I'm asking you guys to follow on problems like this. It's left endpoints. Draw a sketch. Show yourself that this would be what, an overestimate or an underestimate? Severe underestimate, okay? Now draw in the rectangles. Draw these little lines underneath to help remind you that you are using left endpoints to find your heights. Your heights go here. Now calculate the area of each rectangle. The width of each rectangle is 1/2, right? Yeah. Okay, so go 1/2 times each one of these numbers. Well, 1/2 times 0 is 0. 1/2 times 1/8 is 1/16. 1/2 times 1/2 is 1/4. And then 9/8 times 1/2 is 9/16. What we have sitting here is all of the areas of all of the rectangles that we just formed. So to find the area, we just add all these numbers together. Now, you can do that in your head. It's not that big a deal. We have 16ths, 4ths, and 16ths. If I change this to 16ths, it would be 4/16, and now just add across. 1 plus 4/16 is 5, plus 9/16, 14/16, which is 7/8 is my answer. It's very inaccurate. It's definitely an underestimate. Definitely an underestimate, okay? We know that. But if the problem says calculate the area using left endpoints in 4 rectangles, this is the answer. Yes. Okay, let's do the same thing but using right endpoints this time. So right endpoints means the right side of the rectangle will go up and touch the function. We have the same. Guess we'll do it next time.